Okay, so now I will be discussing maybe so far we have been dealing with the scientific aspects, but now I will take you to the little different aspect, that is from the aspect of uh, trajectory design, that is how to go to the point where we can do some scientific research. So I will be discussing on Lagrange point as a vantage point in space-based exploration and future opportunities. And as I understand the diverse background of people who are attending this, therefore, I have just made the presentation in such a way that I have just covered all the prerequisites necessary for this and in the simplest way possible. Otherwise, it's a very complex subject in the sense, and but I have tried to avoid all the equations and all those things, and so that to put it all missions things in a very simple perspective. Okay, so this is just a general outline of my presentation. So I will be covering some prerequisites. Sometimes many of the people would already be aware of those things. Just repeat them as fast as possible. Then other will be Lagrangian points, three-body problem, which is the main topic. Then what is the dynamics behind it? And then we will go to the application of them, and then missions, and then future point of utilizations. Okay, so we are all aware of the Newton laws of motions. Actually, everything right from the base I'm starting, whichever is used in the foundation for the study of this subject. So Newton law, we already know that Newton first law of motion says that object at rest will stay at rest and object at motion will stay in motion unless acted by an unbalanced force. Balanced force, no problem. Similarly, Newton's second law says if greater the mass, greater the force is required. And Newton's third law says that for every action, there is always an equal and opposite reaction. This is widely used in our launch vehicle. Our launch vehicle go by this principle only. Then important thing is law of universal gravitation. We know that by this law, which says that every two particles of matter in the universe attract each other with force, which is equivalent to F is equal to gmm by r square. And from there only, actually, we are getting our gravity coefficient, gravitational coefficient. For example, all we are aware that for Earth, the gravitational acceleration is around 9.81. And similarly, we can see in the table comparison for the other one. We know that for Moon, it is around 1/6 of the Earth, and Sun, it is around 273, and Jupiter around 26. For Mars, around roughly 1/3, we can say. So this is the implication of this gravitational constant. Then other important thing is that Kepler's law of planetary motions, even though we say that Kepler law of planetary motion, but it is very well applicable to the Earth satellite also, and any other bodies which is gravitating body, there also it is applicable, but it was discovered for the planetary motions, basically from the Tycho Brahe data, over which possibly Johannes Kepler made a intelligent fit, and from there he derived these fundamentals. The first one is that orbit of planets are in ellipses with sun at one of the focus. We know that circle is a special case of ellipse, so sometimes circular orbit also we can see. Similarly, planet move faster when it is closer to sun and move slower when it is far from sun. So we can see that when it is satellite is at nearer point to the central body or gravitating body, at that time it will be moving very fast because it has to cover equal areas in equal time. So that is the reason when it goes nearer, it goes faster. When it is further, it goes slower. Then the third one is the important one, which says that the square of planet orbital period is proportional to cube of its average distance from the sun. Because of this, what happens is the objects which are nearer, you will be seeing that they are moving much faster as compared to the objects which are further. So planets in large orbit take much longer than the planet in small orbit to complete one revolution of any gravitating body. For here example, sun is there. Okay, so our important aspect is the three-body problem, because Lagrange pointed out the fundamentals of three-body problem. So three-body problem, what it says is that suppose you have three bodies, all are having gravity, then what will be the motion? Actually, this is a very complex problem and it lacks general or closed form solutions. Why it is complex? Because of the non-linearity and chaotic behavior also, because even a small change in initial conditions can lead to wide variation in the result. Now, why it is not solvable is just this table shows that, for example, suppose we have a two-body problem is perfectly means is analytically solvable. We have the analytical solution for this two-body problem because it is having degree of freedom 12 and integral of motions also we get 12. 12 because this 4 in each coordinate, x coordinate, y coordinate, z coordinates. So 4 in each coordinate. So we get around 12 degree of freedom. But for the three body problem, it is around 18. 18 degree of freedom is there for three body problem, but we are having only 10 integrals of motions. So therefore, this is not analytically solvable. So we have to go numerically only here. Similarly, for the other things also, which I will be covering in my presentation. Similarly, restricted three body problem and circular restricted three body problem. But before that, what is so? It is well understood that restricted three body problem is very complex and not solvable. But if you see our most of the natural solar system and other aspects, they are not perfectly three body problem. They can be simplified in certain ways. For example, if you see Earth and a satellite, you can see the satellite will have considerably negligible mass with respect to Earth. Or if you have Earth, Moon, and satellite system, Earth and Moon will have a very large mass as compared to satellite. So we can say satellite is not at all imposing any gravity on these two planets. So when we take such problem in such a way, we say that it is a restricted three body problem. And if we assume the orbits, that is the primary movies, that is the larger bodies. For example, whether if you take Earth Moon system, Earth is a bigger primary, then secondary body is Moon, and we have a spacecraft. And if we say that Earth and Moon are moving in a circular orbit, then around their barycentric, then we can say that transform this problem into a circular restricted three body problem. This was actually a very important problem, which was contribution for solving this problem in the sense that not perfectly solved, but we could get some stationary points or equilibrium points due to the contribution of following people like Poincare, Hamilton, Euler, Laplace, Lagrange, and Jacobi. Actually, Euler was the first person in 1767 when he could find three equilibrium points. And similarly, later on, after 5 years later, the two extra equilibrium points were found by Lagrange. Then in 1836, Jacobi was a person who said that, like in a two-body problem, we say that energy is conserved. Similarly, Jacobi said that in a cyanotic frame, that is a rotating frame, if we transform these equations, there is a constant called Jacobi constant, which is also remain conserved. This was very important development. Then in Poincare further added to this, and he said that around these stable points, we can have periodic orbits, and we have some stability and qualitative characteristics for them also. Okay, so now we come to circular restricted three body problem. So it says that, as I already told you, that we are having three bodies, but one of the body is actually so negligible that it is not imposing any gravity on the other two, and it assumes two primaries. For example, it can be Sun Earth, it can be Sun Jupiter, it can be Earth Moon. Like that, any system you can take it, and we assume that they are moving in a perfectly circular orbit around the center of mass, or barycenter, you can say. So if we impose the problem like that, and we solve this problem in a rotating reference frame, then we can see that the body's motion will be like this. It will be having some peculiar solution, like green dots are nothing but the stationary solutions, which I'll be covering in later slides. And it will have some forbidden zones also. That is, it will define the zone of spacecraft motion beyond which it cannot go. You can see whenever spacecraft touches this line, it turns. So it will not go beyond the other region in any way. So as earlier told that this defines in circular motion on Jacobi constant also, it defines forbidden regions, and it defines the existence of equilibrium Lagrangian points with orbit around them. So now, important concept for that, why these things happen is, then whenever we go to rotating frame, there are two Fixious forces which come into picture, and I call them Fixious forces because physically we can't measure them. For example, one is centrifugal force. For example, if somebody is tying a stone to this thread, then we know that there is a tension force on the thread. But when it is rotating in the rotating frame, if you see, then what will happen is that has to be balanced by some force. So for that force only, we assume that it is a centrifugal force which is balancing it when we observe this motion in a rotational reference frame. And similarly, Coriolis force and this centrifugal force actually depends just purely on the angular rate of your frame, the rotating frame, or so whatever rotating frame axis you are taking, what is the rotation rate of that, that is omega, and where it is located, that is r, its position. It is not dependent on velocity. Now, if you come to Coriolis force, it is also arising from the rotating reference frame. But what it does basically, it tries to deflect the state motion of the object, and it is purely dependent on the rotation rate of the axis and as well as velocity of the particle. For example, it is not dependent on position. You can see here clearly. And you can see this red line is nothing but a, if you see it inertially, you will find the object moving like a red line is moving. But if you see it, if somebody is sitting in the blue dot, then or yellow dot, he would see the motion going like this in that curved trajectory. So the Coriolis force deflects an object of mass to the left side in a frame of reference with clockwise rotation, and right side in the frame of reference with anti-clockwise rotation. One very good example with which we can associate this is our, whenever this Coriolis force effect, we can see that cyclones and other things. You will see that in northern hemisphere, they will be having clockwise movement, but in southern hemisphere, they will be having anti-clockwise, or they will be showing anti-clockwise motions. Okay, so now we discussed that there are 5 equilibrium points. What is the meaning of these equilibrium points is, 1 minute, I will just try to demonstrate it with the, okay. So there are where this centrifugal force will balance the gravitational force. We know that gravitational force is acting. If you consider this just a snapshot of a rotating frame, in the rotating frame, suppose you are having any plan, this L1, L2. So these are the stationary points like L1, L2, L3, L4. These are the equilibrium points which we said that come from the solution of a circular restricted 3-body problem. And in actual, this will be rotating like this. Here 1, 2, 3, 4 are nothing but the L1, L2, L3, L4 only. And we can see that they are rotating among a central body. Basically, they rotate around the barycenter of the system. But one thing, as I discussed earlier, when I said that if further the planets from the central body, the slower they will move. But here, each point, if you see 1, 2, 3, 4, this Lagrangian points, this L1 and L2, even though they are, one is nearer to the sun and other one is further from the sun, Earth from the sun actually, from sun L1 is nearer and from sun L2 is further. So by Kepler law, basically third law, L1 should move faster and L2 should move slower, isn't it? But in actual, what happens is these both are moving with the same rate as of Earth. How this happens is I will explain in my next slide. Similarly, L3, L4, L5, even though they may be looking on the Earth orbit, but they are slightly displaced, maybe some 600 kilometers. Even though being 600 kilometers away, still they maintain the same rate of Earth. You can see from here, same rate of Earth. So what is the reason for that dynamics is, I will just explain here. Suppose you take, this is by Kepler, they are perfectly following the Kepler law. So here what we are assuming is Earth is not imposing any gravity on the spacecraft. So when that is the case, spacecraft will be much moving faster than the Earth, and Earth will be moving slower. Now, but it is not the reality. Actually, Earth is imposing the gravity. Now, what happens is when you take Earth into consideration, the spacecraft at L1 gravity gets, actually this you can see that Earth gravity is acting this side, and sun gravity is acting this side, and sun gravity on Earth is also acting this side. So basically, effective gravity on satellite becomes sun gravity minus the Earth gravity, and because of that, what happens? It is supposed to move. It is supposed to move faster, but then its motion gets decreased because of the additional gravity component coming from the Earth. And in result, what happens that both of them start moving with the same angular velocity. Similarly, we can see for L2 also, they will be moving faster, but when spacecraft is at L2, it is supposed to move slower, it is moving slower. That is perfect. But if you take the gravity of Earth, it will now, what happen is Earth gravity will be acting in direction, and basically it will be enhancing the gravity of the spacecraft. So in that case, what will happen is effective gravity on satellite becomes sun gravity plus, actually it should be plus. I'm sorry, sign is wrong, I think. So what will happen in that case when it increases the gravity? So your spacecraft starts moving with the same as Earth. That angular velocity becomes similar. Okay, so here both are adjacent, so your gravity is enhanced here. Now, one of the important aspect I had told earlier, the discovery of Jacobi integral. This says that there is a integral of motion in circular restricted 3-body problem, which is called Jacobi constant, and you define the coordinates of any spacecraft in the 3-body system, and it will have a fixed Jacobi constant throughout it motion. And this Jacobi integral states that conservation of kinetic energy as well as potential energy in the rotating reference frame. And this only defines zero velocity curves. This means that these curves define the boundary of a spacecraft beyond which it cannot move. So it will be bounded by this zero velocity curve. For example, if you see here, any spacecraft in this dot will go up to this point only, and again it will come back, because after that its velocity will become zero, and therefore it has to return back. So potential energy will become maximum, like in two body it happens. Similarly, suppose some spacecraft is here, it cannot cross these boundaries. So like that, we are defining these energy domains. So these curves can be closed around M1, M2, or sometimes they can be open based on the basically the masses, how the mass ratio of primary body and secondary body. For example, suppose Sun is there and Earth is there, so their mass ratio will decide whether these realms will be open or closed here. So these curves cannot be crossed during the motion. Now, because of this, we define the Hill region. Hill region, basically what it tells is the region forbidden, defined forbidden and allowed region for the motion of the spacecraft. So, for example, if spacecraft is having sufficient energy, which is less than the energy required to be at a first Lagrangian point, then what it will happen is it will remain inside that Lagrangian point only, nearby periphery only it can move. But if you take some point here, it will be here in this domain only. But if it is having energy which is more than the energy required at Lagrangian point 1 but less than Lagrangian point 2, then there will be an opening here, and your spacecraft has larger region to move. But if you further increase the energy, that is, energy is more than whatever energy is required at Lagrangian point 2, or whatever energy is corresponding to Lagrangian point 2, then you can see there is an opening also, and here it will go, and spacecraft can move nearby this periphery also. But if energy is greater than the energy required at L3 Lagrangian point, but less than whatever E4, E5, so it can move everywhere here, but it cannot go near the L4 and L5 points. So this is how these Hill regions define or constant the motion of any spacecraft. So what happened is, now we will discuss the periodic orbits and manifold along this Lagrangian point. So as I already told that this complex interaction of centrifugal force and Coriolis force in centrifugal force and Coriolis force with certain initial conditions. Initial conditions are important. What is the where you are putting with what velocity that spacecraft, that only decides its motion around the Lagrangian points. So we can, if that conditions are correct, then we can get a periodic orbit around Lagrangian points also. And one of the cases like halo orbit, which are three-dimensional periodic orbit in synodic frame, is just half the period of orbital period of primaries. For example, suppose Sun Earth barycenter, if you say that period is 360 days, so their halo orbit period is around roughly 180 days. And this is the orbit where most of the spacecraft around L1 or L2 are put. Now, second concept, manifolds. What happens? The trajectories which will be leading to the halo orbit or which are going out of the halo orbit, generally they are called as manifolds. So manifold are nothing but they are tube of trajectories that are departing or approaching the Lagrange point. These tubes are very important in the application of the Lagrangian point. So a spacecraft can travel around these tubes or in these trajectories with very less delta V, and in fact the change between them can happen with very small delta V. So we can catch one manifold from the other with a very small application of delta V. For example, here this is the unstable manifold if it is going out, and if this is the stable manifold. So for the Earth-Sun system. So any spacecraft, anywhere, suppose anywhere you put the spacecraft, it will automatically go to the Lagrangian points. That is the property of this. And if you put any spacecraft here, it will go out of the Lagrange points. And based on their shape, there are various types of periodical orbits which we consider, like planar and vertical Lyapunov orbit, or Lissajous orbit, or quasi-halo orbits, or halo. Halo orbit basically means perfectly they will be closed, but no such in the actual multi-body framework we hardly get a perfect halo orbit. So we get quasi-halo orbit. That means they will not be closed. They are periodic, but starting point and end point won't meet them. So now we come to the application of, I hope that some basic fundamental which is necessary for the applications I have covered. So now I will come to the applications of the Lagrangian points. So there are, as I already told you, that there are 5 Lagrangian points like L1, L2, L3, L4, and L5. But what are their applications? So one is that solar observation, that you want to observe the sun. You may be observing it for many weather. Sometime many activities are happening at sun. So if you want to get uninterrupted view of the sun, we know that the L1 is a best place to put because it provides unobstructed view. Because if you put any spacecraft around the Earth, it will be eclipsed by Earth every half revolution. But that is not the case at L1. You can see if you put any spacecraft here, even though Earth is rotating or spacecraft is there, that eclipse it cannot eclipse the spacecraft at L1. It can unobstructed view of sun it will get. Similarly, we can have space weather monitoring. From the sun, lot of coronal mass ejections are happening, many indications of space weather because they are affecting the Earth weather also, whatever phenomena are happening at sun. And by putting a spacecraft at L1, it is an ideal location for monitoring solar wind and other space phenomena that can affect Earth, and even such as geomagnetic storm and radiation storms. Another aspect is we can, if you can put some spacecraft at L5 or L3, even though L3 is more impractical than L5, but if you can put some spacecraft at L3, L5, you know that L5 will be coming here. So by and sun is rotating. So sun rotation rate, I think some 40 days or something is there. So suppose some activity happens here. By the time L3 will detect it first, and by the time sun rotates this side, and we will get the information at Earth also. Suppose we are able to put L3. So for that, around 7 days are required by the time sun rotates from this point to this point. So this way we can get early warning system. Similarly, at L5 also, suppose L5 sees some activity here. By the time sun rotates near to Earth, we will be getting the information from L5, and that way we can get some 5 days early warning from this. So this could protect actually critical infrastructure because we are getting very well advanced warning, and therefore we can protect our critical infrastructure like satellite, power grids, and communication network for space weather impacts. Another is that space weather monitoring is very important, as I told, that because solar radiation coming with the coronal mass ejections and flares have high density of high particle proton and electron that are coming near to the Earth environment. Now, because of that, what happened? These geomagnetic storms, it will affect the density of Earth atmosphere. Now we know we are having very important spacecraft in our around the Earth. So any change in the density of the upper atmosphere will definitely guide the lifetime of the spacecraft. So suppose high geomagnetic activity is there, what will happen due to the that atmosphere above, the atmosphere below get heated up and it goes upward, and the density at the upper altitude get increased. And because of that increase in density, your spacecraft's lifetime is going to reduce. Suppose they are debris, they will re-enter, that is a good thing. But suppose they are functional satellite, they will be coming in the lower orbit, or either you have to spend some fuel to raise their orbit again, or sometimes suppose you don't have any, you are working with them, it does not have any fuel, they will perish. One of the very good example of that is SpaceX in 2022. It was about to deploy this 40 of the 49 Starlink satellite, but because of this high solar activity, what happened actually is that the densities suddenly increased of the upper atmosphere, and their lifetime became very less. They did not have sufficient time to raise them because I think they were having low thrust thrusters, and it takes significant time. So they re-entered before they can be deployed. So one of the application Lagrange point missions first to discuss definitely is our own Aditya L1 mission, which was launched in 2023, and it is India's first solar mission. And its objective is also same only, to study the sun. And it reached the halo orbit on January 6, 2024. And you can see the trajectory from the Earth is like this. It goes through space, and then this is the halo orbit. In a halo, even though here it may be shown to you perfect, but it will not be that much perfect. And what happens because of other perturbation coming, there will it is an unstable orbit also. So because of that, you have to do regular orbit maintenance also. So this period is still 180 days. So you have, but that another advantage of this being unstable is that even delta, that is station keeping delta V's also are required very less only. I will just show the trajectory of the Aditya so that you can get into two frames. So here important aspect is one is we observe in the inertial frame. So if you see this trajectory is in inertial frame, it would look like a regular trajectory that is orbiting around Earth. Okay. But if you see this green trajectory, that is the rotating frame trajectory, which will show you the halo orbit. But you won't see the halo orbit in the inertial frame. So please note this, that halo orbit are just a visual perception in the rotating frame only. If you see them in inertial frame, they will be like a regular orbit only, not perfect like a regular Keplerian orbit, but yes, they are also around Earth only. Okay, so this is the way we can see that. So there are other scientific missions also at for solar observation and activities, international missions like Geotail. Geotail is now not functional at all, so I marked it in red. Then we have Wind, it is still functional, but all their objectives are same only. So solar helier objectives, joint mission between ESA and to study the sun. And ACE was launched in 1997. It is a NASA spacecraft to monitor solar wind and its composition. Discover also, it is a monitor space weather and provide early warning. So you can see at present they are using L1 point for the warning, but from L1 to we don't get that much time, because from L1 to I don't remember the number, but maybe very minutes only we will get time for any saving or anything we can do from there. Okay, so now another application of Lagrangian point is that astronomical observation. We all know that L2 point. Now why we go to L2 point for observation is, what if you see here, for this is a James Webb telescope, so we can see L2 point is behind the Earth actually. If you see a Sun Earth line, so it is behind that. So what happens is you get the advantage of a very dark sky on the other side, and it can focus on those areas of the space. And it from one place itself, because now Earth, Moon, Sun, everything will be in one line. So you require very small what you call it, shielding there. So it can shield all the three together. So heat from there. I understand that here some payloads are there which require very less temperature of the cryo level, I think. So it can save from that heat. Otherwise, those payload won't work here. Maybe especially some IRIS or some payload, I don't remember the name exactly. So I think specifically for this one, cosmic microwave background observation, it is ideal location for, because faint afterglow of the Big Bang, the cold environment and stable position minimize interface from Sun, Earth, and Milky Way. Then another application is infrared astronomy. The cold environment at L2 makes it suitable for infrared astronomy, as telescope itself emit less infrared radiation, allowing for more sensitive observations. So this is some images taken by JWST. So you can see how the Lagrangian point 2 can be very useful for astronomical observations. So there are some missions at Lagrangian point L2 also, for example, WMAP, but it is also now not functional. And all are for same purpose only. Planck, Herschel and Planck actually we are launched together. They are both ESA mission, and they are there for detailed observation of cosmic microwave background, which I told you earlier. Similarly, we have a GEA missions, and just here you can see, even though we say perfect, this was not in a halo orbit, it was some type of a Lissajous orbit. So how that orbit looks after so many iterations, you can see here. Similarly, other missions were like Russian Spectre RG mission. This was with Russia-Germany collaborations. Then Euclid mission of ESA also carrying this wide scope telescopes for observing and detecting the distant galaxies. Then JWST already we are familiar with. It has generated a lot of and I think found a lot of I think distant maybe possible life like galaxies or solar systems also. So James Webb Telescope is joint NASA ESA CSA mission, the largest and most powerful space telescope ever built, and it is also located at L2. So another aspect of Lagrangian points is that it can be used for communication. So for example, if you see here, this one thing is understood that whenever three bodies are there, you will have Lagrangian points. So a very good thing is that for every for Sun, Mars you take, or Sun, Earth you take, or all these will have, and their orbit also are nearly circular only. So they are all having Lagrangian point. So suppose you can establish, and as already we know that L4 and L5 are stable points in the Lagrangian, stable Lagrangian points. Therefore, they are actually virtually no delta V is required to maintain them near L4 and L5. So, and therefore it is apt to put them in L4, L5 for communication. But even if we put at unstable point, there also, even though delta V will come into picture, but it will be very, very less, as I earlier told, because of the order of meter per second only. So if we put these spacecraft like this, we can have some type of communications, that is interplanetary communications between different things. So you can see that we can establish a deep space network. For example, this can support a global internet infrastructure. So when we talk about global, we are not talking about the Earth now, we are talking about the solar system itself. And we can have some Mars mission time that will be various relay stations can be established at Mars and Lagrange point, which could support human exploration and colonization effort. And it can help in asteroid mining also. So these are the some very good benefits of these Lagrangian points. So whether somebody has used it or is it just what a theoretical thing. So here is the proof of that, one Queqiao relay satellite that is from China. What it does is it has put a communication, one satellite in Earth Moon L2, and from that it has communicated with the far side of the moon. Actually, we know that they are tightly locked, Earth and Moon, such a way that you never see the other side of the moon. So now suppose you want to have, put some rover that side and you want to have communication with that, it is not possible from Earth. So what basically is done here is we put a spacecraft in the Earth, Sun, Earth Moon L2, and from there we can have communication with the Earth. This was demonstrated by Changpor in the recently there one of the missions. Then another application is that these Lagrangian points, like stable Lagrangian point L4 and L5, since they are stable and they are home for many natural asteroids, natural objects. For example, you can see L4 and L5, especially this Sun-Jupiter system is the strongest L4, L5, because you know Jupiter gravity much more than any other planet. So therefore, any asteroid going, some asteroid getting stuck in L4 and L5, it can't escape there. You can see the green thing. So basically, this is L5, this is L4. So you can see that there are many asteroids in L5, there are many asteroids in L4 also, and they are this we are seeing like this. In they are called as basically trojan asteroids. Okay. So Sun, Jupiter, L4, L5 are containing, I think, millions of these Trojan asteroids. Sun, Earth, L4, as present, I think only two are discovered, like 2010 TK7 and 2020 XL5. But there can be some interplanetary dust captured there, that is established. Earth, Moon, L4 and L5 also is having interplanetary dust and some Kordylewski clouds. Sun, Mars is having four Trojans like 5261 Eureka, and these are the things there. So because of the stability of L4 and L5, these are home to many natural objects like asteroids and other things also. So these asteroids, another aspect, these asteroids have been observed in study for centuries. So therefore, if we can go to any of these asteroids, they can offer very valuable insight into the earlier solar system. Similarly, future application, one another we can see interplanetary superhighway. In this, what we can see is, as I told you, that between these manifolds, if you are connecting the manifold, and suppose you can go between the manifold of all different planets. You have Earth, Mars manifold, Earth, Moon manifold, and sorry, Sun, Earth manifold, Sun, Moon, Earth, Moon manifold, and Sun, Mars, Sun, Jupiter manifold. And I have already told that this connecting them with is very possible with a very small delta V. So suppose we can connect among them, we can establish basically an interplanetary superhighway where we can go from one planet to other with a very less energy. So that is like a expressway where we can where our vehicles will use very less fuel. Okay, so this if as this but only thing is the technology is, as the technology is advancing, the interplanetary superhighway definitely can become foundation for sustainable space travel, enabling humanity to establish interplanetary colonies, explore deep space, and utilize extraterrestrial resources. It represents a shift towards energy efficient, cost effective exploration of the solar system. Then we can think of space colonization also. We know that L4 and L5 is stable point. We can put some big habitat there. And for example, around the Sun, Earth, Sun, Moon, Earth, Moon L2 or Sun, Earth L2. and we can use them for mining resources. We can take resources from some asteroid and then bring it here, and we can do research there, or we can develop new technologies. Similarly, so at present, the point L4 and L5 Earth Moon system has been proposed as a potential location for large space habitat or colonies. So benefit of this are that we know that suppose someday some big asteroid uh, collides with Earth, there won't be any human species. So if we can put some humans here, definitely we can be able to save the human beings. We can definitely acquire resources from all the other sources, for example, from other planets or asteroids or anything, and definitely do some scientific discovery, because once we start developing all these things, it will lead to some scientific degree and technological advancement also. So these are the benefits if we look for the space colonization. One physicist, American physicist, he suggested that in 1974 that Earth Moon L5 could fit several thousands of floating colonies. He has given the shape of those colonies, how to put those colonies, and there are many literature also for this. So future application, another is interplanetary transportation. So these Lagrange point can serve as a stable staging point for spacecraft traveling to other planets. For example, suppose we want to go to Jupiter, other there a very big spacecraft, a very big system is required. We can stage them in a Lagrange point one by one, and once it is completely assembled, then we can go to different planets. So that we can use them for that. So NASA Artemis program actually uses to do such things at Earth Moon L2 point. Similarly, Lunar Gateway at Earth will serve as a hub for lunar exploration and stepping stone for future Mars mission. So this basis can provide facilitating crew transfer for missions involving multiple planets, and they can serve as a logistic for gathering team before they set off and their interplanetary expeditions, just as discussed. And we can basically extend operational lifetime of other systems also. Suppose we have some fuel and other thing we can put at L2, and our systems we can refuel there. So what are the overall this future of Lagrange point learning, how we can unlock the next presentation? One is that space-based manufacturing. Lagrange point could host manufacturing facilities for building and repairing spacecraft in space. We can have a space tourism. Lagrange point could be destination for space tourism, offering breathtaking views of cosmos. Then we can have resource efficient Lagrange point. Lagrange points could serve as a base for mining asteroids and other celestial bodies for valuable resources. And scientific discoveries, like they can unparalleled for scientific exploration and discovery that we already understand when we go there. But what are the challenges? Basically, like thermal, environmental, communications, instability, and cost. So thermal, because temperature will be very high at this Lagrangian point, so we need to have a good thermal protection system based on the, and this thermal requirement will vary based on the proximity to the sun. And environmental effect, because there are many forces acting there, gravity, solar radiation, pressure, so our orbit will keep on diverting, so we have to maintain that orbit. So therefore for that orbit maintenance may be required. Sometimes we have to save them from micrometeoroids or maybe some space debris also, that also need to be considered. Similarly, communication and data relay, because their distances, we have to see that communication is happening properly or it's not occulting with any other celestial objects. Or instability, already suppose since we are putting that in unstable point, we will have to do timely station keeping or orbit maintenance maneuver also. And of course cost also is important factor, because reaching this Lagrange point, especially stable one, requires very high energy and therefore very high launch cost also. So I conclude my presentations here that Lagrange point, they hold significant potential for future space exploration and utilization, and these locations in space provide a platform for scientific research, space missions, and potentially even space settlements. Thank you.